Hello. The topic of today's lesson is techniques of integration. During these lectures, my main goal is to improve your skills in computing integrals, which is actually a very important part of this course, one variable calculus. It's not only needed for this course, but if you are supposed to go to the next course, multivariable course, you really need to have good skills in computing integrals. Of course, during the first two lectures, I want just to present the main concepts and definitions and ideas about this topic. And in my presentation, I will be a little bit more precise than the standard course book on the one variable calculus. But of course, by no means I will go to the level of advanced calculus or mathematical analysis. But after two sessions is finished, my main concern will be to come back and improve your computational skills regarding integrals. And below this video and the coming videos, hopefully, you will find the link to the PDF file, which contains some problems and exercises for you based on the lecture that you see now. In principle, you should be able to solve those problems, and my goal is to do my best to be able to provide another video for you in which I go through all those problems one by one and describe them. And in case that you don't know how to solve them, by watching those videos, you will be able to understand how the solution is. Okay, so the first thing that I want to introduce today is actually the notion of a primitive function or an antiderivative. And as I told you in my presentation for this definition, I will be a little bit more rigorous than the one given in the book. So let us go to slides here. Okay, the first thing that we want to do is go through the definition of a primitive function. So let D be an interval or the union of finitely many disjoint intervals in R, and let little f be a real valued function with domain D. That's the same D here. A real valued function capital F with domain D is said to be an antiderivative or a primitive function of f on D if capital F is differentiable on D and capital F prime at x equals to f at x for every x in D. Okay. Let us try to understand the ingredients of this definition together. So here D is an interval or the union of finitely many intervals. Now let us try to understand this definition sentence by sentence. Okay, so what do we mean by an interval? So you know that if A and B are real numbers, such that A is less than or equal to B, you can talk about the closed interval A and B. We put square brackets around them. What do I mean by this? This is a shorthand way of writing this longer definition of set. This is the curly bracket, means the set consisting of all numbers x belonging to the set of real number such that A is less than or equal to x less than or equal to B. That's called a closed interval. And of course, what happens if A and B are equal? If A and B are equal, then this becomes the set consisting of all real numbers such that A is less than or equal to x less than or equal to A again, which of course means that this is the set consisting of one element, and that is A itself. That is called a degenerate closed interval. In my presentation, I'm not going to consider these type of intervals. So this is one type of intervals that I will allow to have it here, but not that interval. We also have another type of interval, which is called an open interval. So, and it is a little bit unfortunate symbol, because this is the same symbol we used for an ordered pair with components A and B. But here I am using it as an interval. What does it mean? It means that it's also a set X belonging to the set of real numbers such that A is less than X less than B. The difference is that the closed interval contains the endpoints, includes the endpoints, but an open interval does not contain the endpoints. It's excluded from them. And what happens if these numbers are the same? So then it means that this is the set of all real numbers such that a is less than x, less than a. Of course, there is no real number with that property, which is strictly larger than a and strictly less than a. So this means that nothing is left for us to put in, and that is called the empty set. Okay, that's also a degenerate case. I will want to exclude these kinds of intervals from my discussion. So that is another interval that I will consider here. These intervals can be combined. For example, I can consider semi-open, semi-closed intervals like this. So I hope the idea is clear. This is the set of all x's between a and b. A is included, b is excluded, and this is the other way around. So these four intervals that you see that I have written here are actually come under the title of bounded intervals. Bounded means that you can find a number which is greater than all elements of that interval. You can also find a number which is smaller than all elements of the interval. Yes? So this is also included in my discussion. That is also included in my discussion. But we can also consider unbounded intervals. For example, we can consider this scenario that I have something like this. This is also an interval. Yes? What is the meaning of this? This is the set of all real numbers such that x is greater than or equal to a. So it starts from a, includes a, because I put this square bracket here, but there is no upper bound for it. So that's an unbounded interval. It is unbounded from above, but of course bounded from below. Yes? I don't know, you can consider this scenario. For example, minus b up to b. Let me put parentheses here. So this means that this is x in R such that x is less than b, and it is not including b because I've put these brackets here rather than a square brackets, okay? And so this is also an interval, but this is an interval which is bounded above but not bounded below, okay? And in the extreme case, I can consider this one, an interval from minus infinity to infinity, but this is just simply the set R itself. So these are cases of unbounded intervals. We will consider these also in our cases. Okay, so this is the notion of interval that I want you to know. What is the main property of an interval? The main property of an interval is this. Any kind of intervals that I told you it is allowed for our discussion, the property is this. If you, for example, let me consider one interval. So it's, for example, it starts from here, includes this point, excludes that point. So let me write it from 1 to 7, for example. The main property of this interval is connectedness. The connectedness, what does it mean? It means that whenever you pick up 2 points there, any 2 points in your interval, then your interval contains all the line segments between those 2 points. So that is the importance of the intervals. Yes, so that's the important thing. So it doesn't matter which interval you are considering, except these degenerate cases. That is the main property that makes intervals so important for us in this topic. Choose any 2 points within the interval. All the line segments between those 2 points is also included in that interval. Okay, now if you go back to slides, so the D here that I have mentioned, I am assuming that D is either an interval itself or it is the union of finitely many disjoint intervals. Okay? So for example, let me use the symbol I for interval. So I'm assuming that D is either one unique interval or it is the union of finitely many intervals. So let us say that n intervals. And this symbol means union. So the union means appending these numbers, these sets together, okay? But I'm not allowed to repeat the repeated numbers. For example, if I tell you that I1 is the interval from 1 to 3, and I2, for example, is the interval from 2 up to 5, and if I ask you what is I1 union I2, so that is easy to understand. What does it mean? It means that the set consisting of all elements in R, which are either in I1 or, this symbol means or in I2. But of course, in mathematics, when you say or, this is an inclusive or, so it means that either this one, not that one, or this one, not that one, or both. Okay, so what is that one? So if you want to understand that, so for example, you can consider that this point 1 and then 3 is excluded. So I put a hollow circle to show that I am excluding this. So this is a representation for that. And then here is 2, so I have to make 2 excluded. So let me just not disturb this one. Start from here. Okay, sorry. 2 is excluded. So that's 2. And then we go up to 5. For example, let us say here is 5, and then this is included. So if I ask you to union them, it means that I am interested in all real numbers which are either in this one or in that one or both of them. So it is not that hard to understand that the union goes from 1 up to 5. Yes? So again, the union of these two intervals is actually another interval. And are these intervals disjoint? No, the disjoint means that they are not supposed to overlap. Because if they overlap, it's not a, by the way, it's not a very big constraint, because you see that even if they overlap, when I union them, I can write them as one single interval. Okay, so disjointness is not a very big constraint, because if you have a union of intervals, you can always write it as union of disjoint intervals. Okay? Okay, so here, what I mean that you assume that D is an interval, one single interval, or a union of disjoint intervals. So if I want to show the disjointness, I would say that I sub I intersection I sub j is the empty set for all I and j in the set of 1 up to 2 up to n. Of course, I is not equal to j. Okay? But I don't want to disturb you with these notations and symbols. So simply saying that D is the union of intervals with or disjoint. Okay? Okay, so now you have a good picture of what does it mean. But now what is f now? Little f is a function whose domain is this set. So its domain is either one single interval or the union of disjoint intervals, but the codomain is R. So this is what is called the real valued function. A real valued function is a function whose output is a real number. So this function takes a number from D and gives a real number back to you. So that's a real valued function. So let us consider two real valued functions with the same domain D. One of them little f, the other one capital F. We say that this capital F is an antiderivative of little f if there are two conditions satisfied for the capital F. The first condition is that the capital F is differentiable everywhere in D. Moreover, for every value in D, for every element in D, x, say x, the derivative of capital F calculated at that point coincides with the value of little f at that point. So let me repeat. So the definition tells you that the capital F with the same domain as little f is called a primitive function or antiderivative of little f if, first of all, the capital F is differentiable everywhere in D. Moreover, for every x in D, this means for all x belonging to D, the derivative of capital F calculated at that x matches with the value of little f at x. So if this is satisfied, we say that capital F is a primitive function for little f. So if I want to, roughly speaking, to just say something for yourself to remind it, we say that capital F is an antiderivative of little f if the derivative of capital F matches with little f. But of course, this is not exactly what is supposed to be, but that is something that you can rely on to remember the main definition. Okay, so might be that's a good idea if I go to a very, very simple example first. Okay, consider little f, the function little f, defined on R by this rule. F of x is 3x squared. Three functions, capital F1, capital F2, and capital F3, also defined on R by these rules. Yes, f of 1x, f1 of x is x cubed, f2 of x is x cubed minus 5, f3 of x is x cubed plus square root of 7, or all antiderivatives of the function f. Why is that? Because all these three functions that you see here are differentiable on R. Moreover, if I differentiate them at a given value x in R, all of them, the derivative of all of them at x is equal to f at x. So if you differentiate x cubed, it becomes 3x squared. If you differentiate x cubed minus 5, it becomes 3x squared. And the same is true for this one. But that's a very, very simple example. Okay, now let us go to a little bit more interesting example. We want to show that function capital F defined on R by this rule is an antiderivative of the function little f defined on R again by this rule that you see. F of x is equal to 1 over square root of x squared plus 1. Okay, so let us just do it here on the board. So the function f of x is given to be ln of x plus square root of x squared plus 1. And then the function f of x is given to be 1 over square root of x squared plus 1. It is mentioned in the problem that capital F is defined on R. So this means that R, as you see here, R is also an interval. So here D is equal to one single interval, and that is the set R. Okay, we want to show that this function, which is defined on R, is an antiderivative of this function, which is also defined on R. So how should I prove that? I would say that let x be in D, means here in R. We show that f is differentiable at x. Moreover, we show that its derivative at x is equal to f of x. So actually, this is an exercise in differentiation. The primitive function is proposed to you, and you're supposed to confirm that this is an antiderivative. So what we do, we just differentiate. How should I differentiate? So I need to remind you about this formula. So you know that if I have ln of u is a function of x, wherever u is positive, of course, because otherwise ln is not defined. If I want to differentiate it, it becomes u prime divided by u. So you had this in the previous lessons. Okay, so here I give the role of u to this expression, and I calculate f prime of x. So how should I do that? F prime of x is equal to, according to this rule, I need to repeat u in the denominator. And then I have to write the derivative of that in its numerator. Of course, for the denominator, I just copy and paste. Nothing should be done for the time being. And then I start differentiating this one. The derivative of x is 1, and for calculating the derivative of this one, I use this rule. So the derivative of the square root of u, where u is a function of x, is just u prime over 2 square root of u. So then it becomes plus 2 square root of u. I am giving the rule of u to x squared plus 1. So this becomes 2 square root of x squared plus 1. And the derivative of x squared plus 1 is just simply 2x. And then you realize that these 2 and that 2 are canceled. And what I do, I take the common denominator here. So this becomes square root of x squared plus 1 plus x divided by square root of x squared plus 1. What I have written here is just 1 plus this is left, what is left there, and then divide by the whole denominator here. And then you immediately realize what is going on, because this one is exactly what is happening in the numerator. They are canceled. What is left for me is this expression, and this expression is exactly f of x. Okay, so I was able to show that this is an antiderivative of that function. Of course, you know that in the future, the main goal of this lesson, techniques of integration, is how can I derive this if this is given but this is not given. So you see that if an antiderivative is given, it is easy to confirm that because you just need to know how to differentiate that function mainly. Okay? Okay, so now let us go to the next example. So here, we want to show that the function capital F defined on the open interval from -2 to 2 by this rule, 1 over 2x times square root of 4 minus x squared plus 2 times arc sine of x over 2 is an antiderivative of the function f defined on the same open interval, but by this simpler rule, f of x is equal to square root of 4 minus x squared. Okay, so let us go back to the board. Okay, so here, capital F is defined on the open interval with this rule, and little f is defined on the same open interval with that rule. We want to show that this is an antiderivative of that function. Okay. And I want to discuss, so let me solve that problem, then I will come back to see, talk a little bit about this open interval here. Okay, so what we need to do, again, to confirm that, I need to show that the derivative of this given function is that function. So to do this, I need to use this formula for that part. Of course, that's a product, so I also have to use the product rule, which is this rule. So if I have f times g prime, it is f prime times g plus f times g prime. But also, I also need the formula for the derivative of arc sine. Hopefully you remember that. If you have arc sine of a function u, of course, if u is between -1 and 1, strictly, then this is differentiable, and the rule is to write u prime over square root of 1 minus u squared. So you see that in order this function to be differentiable, this u should be strictly between -1 and 1. Okay, even though the function arc sine is also defined if u is equal to 1 and -1. But if I choose u equals to -1 and 1, the function is still defined, but because the denominator becomes 0, the function is not differentiable. And that is the reason we have to choose open interval rather than a closed interval. Okay, I will come back to this and explain it. Let us just try to solve the problem. Okay, so what I do, I start differentiating this function. So this is a product rule. The derivative of the first one is just 1/2 multiplied by the second function itself, plus the first function, which is 1/2 x, multiplied by the derivative of this function, which I use this rule here. U prime, I give the rule of u to this expression, u prime becomes simply -2x, and divided by 2 square root of u, which is that expression. And then for this one, I give the rule of u to x over 2 and use this formula. So I have a constant 2, and then I will have square root of 1 minus x over 2 to power 2. So as I told you, I gave the role of u to x over 2, and then I have u prime. But what is u prime? U prime is just simply 1/2. And now my duty is actually to simplify this and show that this expression coincides with that expression if x is somewhere strictly between -2 and 2. Okay, so that's just simple algebra. So let me just copy and paste the first part, which I cannot do anything for it. But here you can see that this 2, for example, and that 2 are canceled. This x is being multiplied by minus x. So this becomes minus x squared. And then what is left for me is a 2 here. And I have 4 minus x squared. Here, these 2 and 1/2 are canceled. So here, this is x squared over 4. Okay? Okay, if I go a little bit further, before doing that, let me simplify the last term a little bit more. So I copy and paste the first 2 terms. And then if I take the common denominator here, the square root of 4 is 2, so it goes up to the numerator. So I will get that. Now everything is ready, so we can simplify that. Between these 3, I take the common denominator, which is the denominator of the middle one. So I will take 2 square root of 4 minus x squared here. I divide this in my head with the denominator 2. So this is left. This should be multiplied into the numerator. So this becomes 4 minus x squared. Then I have a minus sign here. This I divide it in my head with this one. That's 1 time. So that's just minus x squared. And when I divide this in my head by that, it is 2 times. I multiply it here and the sign is positive. Okay, so what happens here? 4 and 4 becomes 8 minus 2x squared. And then I have 2 square root of 4 minus x squared here. In the numerator, I can factor a 2 out. So it is 4 minus x squared, yes, divided by 2 square root of 4 minus x squared. And then simply this one and that one are gone. 4 minus x squared can be viewed as 4 minus a square root of 4 minus x squared, the square root of 4 minus x squared. Why? Because x is between -2 and 2, and this expression is positive. So this is exactly equal to this expression. But one of them and this one are gone, and one of them is left. So hopefully you realize that this is exactly what I want, which is exactly the function f of x as you see here. So the question is that, can I change this to -2 and 2 and change this to -2 is 2 and say that this is an antiderivative? This new function with the new domain is an antiderivative of that one. The answer is no, because even though the capital F with this new domain is also well defined, because if I put 2 or -2, I do not have any problems here. This simply becomes 0. And if I put 2 or -2 here, this becomes arc sine of 1 or -1. Both of them are defined. And same story here. That's also defined. But still, I cannot say that the capital F defined with this new domain is an antiderivative of little f with that domain, because these functions are not differentiable. This function is not differentiable at this point or that point. Okay, so we have to use the open interval. Can I make my interval smaller? The answer is definitely yes. For example, can I say from, I don't know, from 0 to 1 and make this one also from 0 to 1? Yes, the answer is that. The answer to this is yes. But I cannot go beyond that, okay? Okay, so let us go to another example. It's a little bit more interesting example. So the algebra is not that involved as the previous case, but I like this example more, okay? So show that the function capital F of x defined by 1/2 x times absolute value of x is an antiderivative of the function f of x equals to x, absolute value of x on R. Okay, so this is our goal. We want to show that this capital F defined on R by this rule is an antiderivative of the famous absolute value function, the function defined on R by this rule. Okay, so I need to show that this function is differentiable everywhere in R and its derivative at any real number matches with the value of this function at that number. Okay, so what we do, hopefully you know that whenever we are dealing with absolute value, usually we have to get rid of that absolute value more or less immediately. So let me just rewrite this function slightly differently. So if x is positive or 0, you know that the absolute value of x is equal to x, and if it is multiplied by another x, it becomes 1/2 x squared. So this function is 1/2 x squared if x is 0 or greater than 0, and if x is less than 0, the absolute value becomes negative x. When it's multiplied here, it becomes -1/2 x squared. So this function can be written as one single rule using the absolute value sign, or written separately with two different rules based on which condition you have. And then we want to show that this is differentiable and its derivative is equal to this one. This is different. Of course, if x is strictly positive, the function f of x is just a simple polynomial function, it's differentiable. And if x is negative, again, the function is a polynomial function, it's differentiable. Okay, so that's simple. So let us just do that. So let us consider x is positive. So then what happens? This means that capital F of x follows the first rule. So then it means that it is not only differentiable, but also I know how to differentiate it. When I differentiate it, it becomes x. So the derivative of that one is x. But what is little f of x? Little f of x is absolute value of x, but I am considering the positive value for x, so that becomes x. Now compare this one with that one. If x is positive, little f of x is x. Capital F prime of x is also x. So this means that under this condition at least, f prime of x is equal to f of x. This is correct if x is positive. Yes? But what happens if x is negative? If x is negative, then what is capital F? If x is negative, capital F is this one. It's -1/2 x squared. So it is not only differentiable, but its derivative is simply calculated to be -x. But now let us see what happens for little f of x. If x is negative, absolute value of x is -x. Okay, so then look at here again. Capital F prime of x is -x. F of x is also -x. So this means that again, capital F prime of x is equal to f of x. Yes, that's also the case if x is negative. So we considered all cases, but still the problem is not solved because we should show that this function is differentiable on R, because the problem itself decided to. So if the problem has excluded 0 from R, if the problem has written -infinity up to 0, by the way, when I say exclude 0, I mean something like this, but this is also it's not an interval, but this is the union of two disjoint intervals. How can you write that? You can write it from -infinity to 0, union from 0 to infinity. Okay, so if instead of R, they have given this as domain, both for this function and that function, we are done. Because we were able to show that this capital function f, so far, is differentiable on this set, and for every choice in this set, capital F prime matches with f, with little f. But now, the problem is not finished yet, because the problem has given R as the domain. So there is one single number that we have to consider, and that is x equals to 0. But I cannot calculate f prime of 0 from this rule or that rule, because depending in which direction is x getting close to 0, I need to consider the left derivative and the right derivative. So the last thing that we have to consider, we need to show that capital F is differentiable at x equals to 0. Moreover, we need to show that capital F prime calculated at 0 is equal to little f calculated at 0. But of course, we know that. What is f of 0? Yes, what is f of 0? F of 0 is 0. Little f of 0 is 0. So in principle, I have to convince myself that the capital F prime of 0 is indeed equal to 0. Okay, how should I do that? I need to remember the definition of the derivative. So the derivative of capital F at 0 is this limit. Capital F of x minus f of 0 over x minus 0 when x goes to 0. If this limit exists, the number corresponding to this limit is the value of capital F prime of 0. But still, we are not sure if this limit exists or not unless we calculate it. So here, the problem is that when x goes to 0, it might be larger than 0 or smaller than 0. What we know is that x is not 0. This is guaranteed by this symbol and the notion of limit. But we don't know if x is greater than 0 or less than 0. And unfortunately for this problem, it matters. Why? Because if x is greater than 0, the capital F follows this rule. If x is less than 0, the capital F follows that rule. So then what we are supposed to do, if you have enough experience in calculating limits, you realize that in order to answer this question, you need to consider two limits. The right-hand side limit and the left-hand side limit. So this is why you are motivated to consider. So this means that x approaches 0 from the right. I need to consider that one. I also need to consider this one for the left. So I need to do it separately. Okay, so let me start with the right-hand limit. So the limit of f of x minus f of 0 over x minus 0, x approaches to 0 from above, from the right side. Okay, x minus 0 is just simply, so let me just copy and paste these parts. And I know that x minus 0 is definitely x. F of 0 is not ambiguous because 0 is using this rule. So f of 0 is actually 0. So I don't need to put this one. But which one I use for f of x? Because x approaches to 0 from above, so I have to use this rule. So this becomes 1 over 2x squared. And then 1x and 1x are cancelled. So this is the limit of 1 over 2x. X goes to 0 from the right, and then you know that the limit is 0. Okay, but now let us see what happens if I calculate the limit when x goes to 0 from the left. So let me change my color here and put it here. Okay, here everything will be the same. F of 0 is still 0 because that is the rule. But f of x, x approaches 0 from the left, it means x is less than 0, so I have to use this rule. So then it means that I will have a, if it is plus as before, but if it is minus, this is now minus. So this becomes plus or minus, this becomes again 0. So it doesn't matter in which direction I'm approaching to 0, from both sides the answer is 0. So the answer to this question mark is indeed 0. So this limit is 0, so this means that the derivative of capital F at 0 exists and is equal to 0, so I was able to show this as well. So this is here the problem finishes, so it shows that this function is indeed a primitive function for that function. Okay, now let us go to the next example, which is the final example for today's lesson. We want to show that the function capital F defined on this open interval by the rule ln of x is an antiderivative of little of f of x equals to 1 over x on the same, of course, interval. Okay, and I want to do something for g. The function capital G of x is defined to be ln of minus x, but the interval that I have chosen is from minus infinity to 0, which makes sense because ln is only defined if the argument in front of ln is a positive number. But the little g of x is still 1 over x, but the domain is from minus infinity to 0. And the third one, we want to show that the capital H defined on this union of intervals by this rule, ln of absolute value of x, is an antiderivative of this function on this domain. The point is, I want you to, this example is a good example, a simple example, but a good example to emphasize that you see the rule of this is the same. So there's the little f follows the same rule, 1 over x, g of x follows the same rule, 1 over x, and even g of x also follows the same rule, 1 over x, okay? But of course on different domains. So they are different functions. So don't consider that little f, little g, and little h to be the same functions. No, even though they are following the same rules, but because the domain of the definition of the functions are different, these functions at the end are different functions. Okay? So let me make the board ready so that I can go back to the board and discuss about this final problem of today. Okay, so this is what we have. We want to show that this capital F, which is defined by ln of x on this domain, is a primitive function for this function 1 over x defined on the same domain. Okay, so our task is to show that this function is differentiable on this domain, and for every choice in this domain, the derivative of the function ln of x matches with the function f of x. Okay, that's simple, because again, you know that the rule of differentiation for ln is u prime over u if, of course, u is positive. So for that choice of x for which u is positive, u is a function of x. So what we can do, we can start from here and then differentiate the function. Okay, so capital F prime of x is just simply x prime over x, so which is 1 over x, and this is exactly f of x. So if I choose any number x in this interval, any positive x, the derivative of capital F matches with the value of the function. But what about this one? Of course, it is clear that I should have a negative sign here because I am choosing negative numbers, and ln is defined only if this argument is positive. Okay, so what I do, I will do the same thing, the same rule. Okay, so it doesn't matter that you have a negative sign here because x is negative, so eventually this is positive. I want to give the role of u to this expression. So what happens? G prime of x becomes negative x prime over x, which is minus 1 over, this is divided by minus x because I gave the role of u to minus x, so I have to write minus x prime divided by minus x. So this is minus 1 divided by minus x, which becomes exactly 1 over x, which is equal to g of x here, if x is negative. Okay, so that's also done. But for the next part, what should I do? I need to use a trick here. So because if I want to discuss about the derivative of absolute value, I need to consider two cases. So let me, to avoid that, let me do this. I will take h of x before differentiation. I will write it as ln. Instead of absolute value of x, I write square root of x squared, because we know that the square root of x squared for all choices of x is equal to absolute value of x. But now what I want to do, I want to give the role of u here, and then I differentiate. So capital H prime of x is equal to u prime, which is the square root of x squared prime, divided by u, which is the square root of x squared. But then I use this formula, square root of u prime is just u prime divided by 2 square root of u. So then it becomes, I give the role of u to x squared. So u prime becomes 2x divided by 2 square root of u, but u is x squared, divided, I keep it like this. And then what happens? These 2 and that 2 are gone. So this x is here, and this square root of x squared will be multiplied there. Okay, but now I write it back. So if I ask you what is the square root of x squared, you will tell me this is absolute value of x again. That's also absolute value of x, which becomes x over absolute value of x squared, but absolute value of x squared and x squared are the same. Yes? Okay, and then they are simplified, and this becomes 1 over x, which is just little h of x. Okay, so you see, if I ask you what is a primitive function for this h, you are not allowed to show me ln of x. You have to show me ln of absolute value of x. If I ask you what is a primitive function for this function, you have to show me that this is ln of minus x. Okay, can you in this case show me this is ln of absolute value of x? Of course yes, because in that case absolute value of x is minus x. Can you write ln of absolute value of x here as well? Yes, because this is positive and absolute value of x is the same x. But the point is that these, even though I write ln of absolute value of x in all of them, but still I cannot say that I have the same functions. Because even though the rules are all the same, but the domains are different, again, the functions are different. So one thing that I just want to say as the final remark is that we said that the capital F is a primitive function for little f if this function is differentiable. So automatically it means that this is also continuous. So primitive functions are continuous as well on the domain that we are working, because by definition they are supposed to be differentiable on their domain, and if a function is differentiable, it's automatically continuous as well. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.